Assalamualaikum warahmatullahi wabarakatuh. We are from group 5 and we going to present to you our finding and solution for problem-based learning. Before we begin, allow me to present our group members. Firstly, Nur Kristina Wardina binti Muhammad Nizal. Second, Nur Syuhada Amira binti Zulkarnain. Third, Farisha Nur Idayu binti Muhammad Jafari. Fourth, Marina Nur Hidayah binti Muhammad Hazli. Sixth, Nur Nadia Natasha binti Khairul Arifin. Lastly, Tuan Nur Safia binti Tuan Lokman.
So, for problem 1, in the Protect Freshwater Lake, environmental research are moderating the population of a specific fish species. This species is thriving due to favorable ecological conditions such as an abundant food supply, clean water, and reduced predations. The fish population was recorded at 2,000 in the year 2015. After 5 years, in 2020, the population increased to 3,500, following an exponential growth pattern. We need to derive the equation represent the fish population at time, which is T. Second, estimate the fish population in 2025. And lastly, predict when the fish population will reach 10,000
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Kristina Wardina. So today I will present about filler table for question 5, part A, about grow and decay. Fact about question 5 is a freshwater lake is a big monitor for fish population growth. Second, the species thrive due to favorable ecological conditions such as abundant food supplies, clean water, and reduced predation. In 2015, fish population was recorded in 2000, and fourth, population is in 2022 is 3,500 fish. And lastly, growth follows an exponential pattern indication continuous increase. For the ideas, firstly, we use the exponential growth equation, which is P bracket T equal to P null E K T. So for PT, which is mean the quantity at the time T. P null is the initial amount at the T equals to 0, and K the growth if K less than 0 and more than 0, and less exponent is for Euler number. Next, for the second, determine the growth rate K using the given data. Third one, apply the equation to the estimate the population in 2035. And lastly, predict the year when the population reach 10,000 fish. So we go for the learning issue. First, we can understand exponential growth model and their application. Second, we can finding growth rates K using a known value. And third one, using logarithm function to solve for time t. And lastly, letting differential equation to ecological study and real world scenarios. Okay, for the last one, action plan or resource need. First, derive the exponential equation based on the given data. Second, calculate the growth rate K. Third one, estimate the fish population for 2035 using the equation. Fourth, determine the time when the population reach 10,000. And last, we need to analyze the ecological application of continuous exponential growth.
We are given the initial fish population was 2000 in the year 2015. This year is taken as the starting point where the time is 0. After 5 years, in the year 2020, the fish population increased to 3,500. We use the exponential growth model to represent the populations over time. The general form of the model is P T equal to P naught multiplied by e raised to the power of kt, where the pt is the population at time t, po is the initial populations, k is the growth rate, and the t is the time in years since 2015. So, first we find the growth rate, which is k. To find the value of k, we substitute the known value into the equations. We set the initial populations, which is PO, as 2000 and the populations after 5 years as 3500. By solving the exponential equations, we find the value of k is approximately 0.1120. So the final exponential mode for the fish population is Pt equal to 2000 multiplied by the e raised to the power of 1.120t. So second, we find the estimate the fish population in the year 2025. To estimate the population in 2025, we calculate the time difference from 2015. Since the 2025 is 10 years after 2015, and we substitute t equal to 0 into our model. After calculating the estimate fish populations in 2025, we got 6130 fish. Lastly, we find the year when the population reached 10,000. We ask to find where the population will reach 10,000. So, we use the same model and set the population equal to 10,000, then solve for t. After working through the calculations, we find that t is approximately 4.35 years. So we got 14 years. Therefore, the fish population is expected to reach 10,000 in the years after 2029.
Okay, so we continue with problem 2. You place a pot of hot soup in a counter in a room with a temperature of constant 20 Celsius, allowing it to cool naturally. Right after removing it from the stove, you measure the initial temperature is 180 Celsius. As the time passes, the soup gradually loses heat to the air surrounding. After 20 minutes, you check the temperature again, it dropped to 100 Celsius. Knowing that the soup will be cool enough to eat once it reaches 80 Celsius. Determine how much time will it take for the soup to cool down from 100 Celsius to 80 Celsius. So, as we see in the problem, we know that the constant temperature is 20 Celsius and the initial temperature when the soup is hot is 180 Celsius. As the time passes, after 20 minutes, it turns to 100 Celsius. So we want to determine how much time will it take for the soup to drop from 100 Celsius to 80 Celsius. So the temperature that is given is 80 Celsius and we want to know what time does it take. So how long does it take for the temperature to drop from 100 Celsius to 80 Celsius? That's all from me.
Alright, we continue for filler table 2. For part B is a Newton law of cooling, question 5. So the fact in question 5 for part B is, firstly, room temperature is constant at 20 degrees Celsius. Second, initial soup temperature is 118 degrees Celsius. After 20 minutes, the soup cooled to 100 degrees Celsius. Fourth, the soup cold following Newton's law of cooling. And lastly, soup is cool enough to eat at 80 degrees Celsius. Okay, for the idea, we use Newton's law of cooling, which state that the rate of cooling is proportional to the temperature difference between object and the surrounding. Second, we use formula T bracket T equal to TE plus T0 minus TE exponent power of negative KT. So for T bracket T is for temperature of the object at the time T. T0 is initial temperature of the object. T is ambition, environment temperature, and K for the positive constant that depend on the properties of the project and environment. So lastly, solve the T to find out how much time it take for the soup cool from 100 degrees Celsius to 80 degrees Celsius. So we move to the learning issue. First, we can understand Newton's law of cooling is application. Second, finding the cooling rate K using logarithm. Third, using the exponential function to solve time to solve for time t. And lastly, practical relevance of heat transfer in food, science and engineering. Lastly, action plan or resources need in Philat Table 2 is first, apply Newton law of cooling formula. Second, calculate the cooling rate K using the initial and 20 minutes temperature data. Third one, determine the time need for soup to cool from 100 degrees Celsius to 80 degrees Celsius. And lastly, you can analyze result in terms of real world applications such as food preparation and consumption safety.
We are
That's all.
given the soup starts at 180 degrees Celsius and the room temperature is 20 degrees Celsius. After 20 minutes, the soup cools to 100 degrees Celsius. So the question is how many more minutes until it reaches 18 degrees Celsius. So first we will use from this formula, which is T of T is equal to TE plus open bracket T naught minus TE times E to the power of negative KT, where T of T is the temperature at time T, TE is the room temperature, and T naught is the initial temperature, K is the cooling constant, and T is time in minutes. So we know the soup cooled from 118 degrees Celsius to 100 degrees Celsius in 20 minutes. So we substitute the value into the formula. We get 100 equal to 20 plus open bracket 180 minus 20 times e to the power of negative 20k. So we simplify, we get 80 equals to 20 plus 160 times e to the power of negative 20k. So we subtract 20 from both sides. That give us 80 equals to 160 e to the power of negative 20k. Now we divide both sides by 160. We get 1 over 2 is equal to e to the power of negative 20k. Now we take the ln of both sides. We get ln of 1 over 2 equals to negative 20k. Okay, solve for k. K is equal to negative ln of 1 over 2 divided by 20. That gives us k is approximately 0.0347. And now we want to find how long it takes for the soup to cool to 18 degrees Celsius. So use the same formula. T of T equals to 20 plus 160 times E to the power of negative 0.0347. We substitute all the value into the formula. We get 80 equal to 20 plus 160 times E to the power of 0.0347. Now we subtract 20 from both sides. We get 60 is equal to 160 times E to the power of negative 0.0347. And next, 60 divided by 160 equals to e to the power of negative 0.0347. Simplifying give us 3 over 8 equals to e to the power of negative 0.047t. Now, take the ln of both sides with ln of 3 over 8 equals to negative 0.0347t. Now, t is equal to ln of 0.3. Then t is equal to ln of 3 over 8 divided by negative 0.0347. Using a calculator, t is approximately 28.26 minutes. So the extra time to reach 80 degrees Celsius is 28.26 minus 20 equal to 8.26 minutes. So the final answer is it takes around 8.26 minutes from the soup to cool from 100 degrees Celsius to 18 degrees Celsius.
For the discussion of this project showed how real-world process can be modeled using first-order differential equations. And for part A, the exponential growth model effectively described the fish population increase under favorable ecological conditions such as abundant food and clean water. The model highlighted how populations can grow rapidly if unchecked, which has implications for ecological balance and resource management. And for part B, the Newton's law of cooling model demonstrated how temperature changes over time in response to ambient conditions. The calculated cooling rate provide insights into heat transfer processes relevant in food science and safety, emphasizing practical applications in everyday life such as determining safe consumption times. Both models illustrated the power of first-order ODEs in modeling dynamic systems across various fields, including biology and engineering. The project enhanced understanding of mathematical techniques like logarithmic manipulation and exponential growth, reinforcing their importance in solving real-life problems.
So for the conclusion, this project shows how first-order ordinary differential equation can solve the real-life problems like fish population growth and soup cooling. We use methods such as logarithmic and exponential function along with database parameter estimation to find unknown value and understand how systems change over time. This example proves the ODEs are powerful tools for understanding and managing both natural and man-made systems. By learning this technique, we gain useful skills for scientific analysis and better decision making in fields like biology, engineering, and beyond. Thank you.